All right, the integral test. So what we'll be looking at here is a few other we're going to be looking at another way to test of a series, whether it converges or diverges. So I'm going to be adding to this list as I go on. But so our tests for convergence and divergence. For an infinite series. So in the previous section, we kind of looked at our first one, right? And our first one was it's called the zero limit test. Or the nth term test. Your textbook calls it the nth term test, but I call it the zero limit test. And if you look back at the video on how to use the zero limit test, that was the first test for convergence of an infinite series. But the integral test is the next, big one we're going to look at. Okay, so note, and I'm gonna add on to this list as we go on. So I'm gonna come back to this and refer to it. But note, the integral test tests. So the integral test tests a series for convergence or divergence by comparing it to an integral constructed from the series terms. So that's the basic idea of the integral test. But so here it is. Here's the actual integral test. So if I'm given a series starting from 1 to infinity of a sub k, I'm given a series, an infinite series, which contains positive terms. Now that's important. The integral test is a series which contains positive terms. I'm going to emphasize that because that's important. Then let f of x be the function you get by replacing k by x in a sub k. So basically all I'm saying here is we replace this a sub k and we just treat it as a function instead. Also, suppose that the following are also true. F of x is continuous for x greater than or equal to 1. So that means that provided this is a positive term series and I replace it with the function, that, you know, this series is continuous for all the values from its starting value forever. So that just means it's continuous. All right. The second thing also must be true. F of x decreases for x greater than 1. What do I mean by decreases? That means the function that would normally be in the series is decreasing for all the values greater than 1 to infinity. It means it's going down, it's decreasing. So if provided this is true, if I have a positive term series, it's continuous and decreasing for all the values on the series, then I could say the following. Then I can have either one of two conclusions by the integral test. If the integral from 1 to infinity of f of x dx converges, then so does the original series. Or I could say if the integral from 1 to infinity of f of x dx diverges, so does the original series. That's the integral test. This right here is the integral test. So, you know, there's a lot to the integral test, it seems. There's a lot of stuff you have to make sure of. So you can't just assume that, you know, you can't just assume that this number 1 and number 2 are true. You have to verify that the conditions of the integral test are true. You have to make sure that it's a positive term series, it's continuous, and it's decreasing for the series. If these three things are true, then you could compute this improper integral. If the improper integral converges, then the original series converges. If the improper integral diverges, then the original series diverges. So there's a lot of steps to the integral test, but that's the basic structure of how you do it. Okay, so let me make a few notes here. So note, you must make sure that the conditions for the integral test are true before you apply the integral test. What I'm saying is you have to make sure that it's a positive term series and it's continuous and decreasing for the series function. You have to make sure that that is true. And then once you do that, then you can apply this. Then you could do this part of the integral test. Okay. So one mistake I see students do is, they'll just immediately, if given a series, they'll just immediately start doing this without looking at these conditions. You have to make sure the conditions hold before you do this. Because if your function doesn't decrease or is discontinuous somewhere, then the conditions of the integral test fail and you can't use it. Alright, so let's look at our first example. And, as we do these examples, I'm going to make some highlights about things you should look out for when using the integral test. So let's go to page number 2 here. All right. Example. Determine whether the series from k equals 1 to infinity of k times e to the negative k converges or diverges. So let's determine if this series converges or diverges. Notice how I don't say use a specific test. It's up to you to decide which test to use. Just like it's up to you to decide which method of integration to use when we did methods of integration back in Chapter 8. You had to figure that out for yourself. Same thing here. Now, granted, we only talked about 2 tests. But you still have to make sure, you still have to check which tests are, best used. So from the previous section I've said, use the zero limit test. Try the zero limit test first. So if you take the limit of this, right? So let's try zero limit. I don't know if it's going to work, but let's try it. So what does the zero limit test say? Take the limit of this series. The limit as k approaches infinity of k times e to the negative k. Well, that's an easy limit to compute. Do that from Calc 1. So you could take the reciprocal here, right? So that's k over e to the k. And if you take the limit of that, that's going to be infinity over infinity, which you could use L'Hopital's rule, which means that it's the limit as k approaches infinity. So take the derivative of k, you get 1, and take the derivative of e to the k, you get e to the k. And if you do that, well, what's the limit of this? Well, e to infinity is still infinity, and 1 over infinity is 0. So remember, what does the zero limit test say? It says that if the limit is different than 0, then the series does what? It diverges. So, if you remember that from the previous section, let me get my notes out here so you can see it for yourself. So here, this was the previous section's notes, right? This right here is the zero limit test. If the limit is different than 0, then the series diverges. However, remember I said down here, it is not true that if the limit is equal to 0, the series converges. If you do get this, you have to use another convergence test. That's what you have to do. So, in other words, the zero limits test says nothing about convergence, only divergence. If you get something that's different than 0, it diverges. Otherwise, the test fails. Now, we get 0 here. So what does this mean? it means the zero limit test. The zero limit test fails. Remember, do not make this mistake. Do not make this mistake. Don't say that this is not true. If you got 0 here, if you got the limit of the series, you get 0, and you say that it converges, that's wrong. You cannot say that. So if you did this yourself and you got 0 and you say, oh, it converges, that's not right. That's not right. You cannot say that. The zero limit test says nothing about convergence, only divergence. Otherwise, the test fails. So we got to try something else. Okay, so, well, we only know other one kind of test. That's all we know. The integral test. So we have to use the integral test. And I'll make a note here. Let me just make a note. Generally, you want to try the integral test when the series looks like something you can integrate. So I'll just say try the integral test when the terms look like something you can integrate. Well, that seems like an open-ended question or an open-ended thing to consider, but that's the idea. You know, a lot of things look integratable, but this one definitely looks integratable. So since this is certainly something like k times e to the negative k, if you think how do we integrate that, we use integration by parts. So since this is something that's integratable, we should try the integral test. All right, so let's try the integral test. So what's the first thing we need to do for the integral test? We have to see that it's a positive term series, right? So are all these terms positive when k starts at 1 and goes on to infinity? Well, so, all right. So for k greater than or equal to 1, because my series starts at 1 and goes off to infinity, comma, I look at k times e to the negative k. Is that going to be positive for k greater than 1? Is it? Well, you know, I could rewrite this as k over e to the k. All right? Now, how do I know this is always positive? Well, if you just look at, you know, the values of k, right? So k is greater than 1 off to infinity, right? So that means k is always positive. And e to the k, well, an exponential function is a positive function, right? If you graph, let me get out your calculator here. So if you do e to the x, right, and you graph that, so e to the x is a positive function, right? So all the terms, so k could be anything. It's going to be, you know, k could be negative or positive, but e to the k is always going to be positive because it's above the x-axis. So e to the k is always positive as well. So because k is always positive and e to the k is always positive, then two positive numbers divided by each other is still positive. So that ratio is always positive. And I could say because k is positive and e to the k, or in this case e to the negative k, if you want to look at it as over e to the k or e to the negative k, same thing, you know, e to the negative k or e to the negative x is just that graph inverted, which is still positive. Right? Still above the positive x-axis, still positive. So it's just, you know, it's just inverted, but it's still a positive function. So you can either look at it as a product of two positive numbers is still positive, or the ratio of two positive numbers is still positive. So because k is positive and e to the k is positive, then you could say either this or this is also positive. I'll just say k times e to the negative k is also positive. All right. What are the next two things we've got to look at for the integral test? So for the next thing on the integral test, the function, so this checks out. So it has to be continuous, and then it has to decrease. Let's look at continuity. So we're going to let, so remember, since this is a positive term series, we're going to let the function f of x replace the series. So instead of writing k e to the negative k, I'm going to write, all right, let f of x equal x times e to the negative x. I'm just replacing it with x instead. All right. So I'm going to let that be true. I could say f of x is continuous for x greater than 1 because I could say this because, you know, what do you know about continuous functions? From Calc 1, you know, functions are continuous on their domain, right? So if I looked at x, what's the domain of x? All real numbers. What's the domain of e to the x or e to the negative x? Here's e to the negative x. The domain is all real numbers, right? So if the domain of this is all real numbers and e to the negative x is all real numbers, then their product is also all real numbers. So it's certainly continuous for 1 to infinity. That's a smaller set than all real numbers. So this is function's continuous for this because the domain of x times e to the negative x is all real numbers. And what you learned about in Calc 1 is that functions are continuous on their domain. Okay, so that part's done. So now I got to show that I've shown this. I've shown it's continuous. Now I got to show the function's decreasing. So how do I know that the f of x is decreasing? Is f of x decreasing? How do I know the function's decreasing? Well, what do you know about the derivative of a function? What do you know about the derivative of a function? Well, what does the derivative measure? The derivative measures the rate of change of something, right? You learned that in Calc 1. So if I have a positive derivative, what does that mean about the function? It means it's increasing, right? So if I have a negative derivative, that means the function is decreasing. So to find if a function is decreasing, that's really just saying, all right, see if the derivative of x is less than 0 for the values 1 to infinity. In other words, for greater than 1. So that's the idea here. That's the idea. When you're trying to show a function is increasing or decreasing, you're just really looking at the derivative. You learn that in Calc 1, right? The derivative is the slope of a line, right? So if the slope is negative, that means the line is decreasing. Well, technically it's the slope of the tangent line at a point, but you get what I mean. So I got to compute the derivative of this function and then show that it's negative for all the values greater than 1 and equal to it. So, all right, so therefore, or I could say so, what's the derivative of that function? So how do you take the derivative of this? Well, you do the product rule, right? High d low plus low d high. So high d low, what's the derivative of e to the negative x? That's going to be negative e to the negative x. That's high d low plus low, right? Times d high. Derivative of x is 1. So if I simplify this a little more, right? So this is going to be negative x e to the negative x plus e to the negative x, right? If I factor this out, if I factor e to the negative x out of here, what do I have left over? I have minus x plus 1, right? In other words, I have e to the negative x times 1 minus x. So that's after I take the derivative and I simplify it a little bit. You know, nothing tricky there. Just taking the derivative and simplifying it. Because, you know, if I stopped here, you can't, you know, how do you know that this is decreasing just by looking at this? Well, that might be a little tricky. That's why I simplified it, because now that it's simplified, you could see that, so you want to see, all right, so therefore, the derivative is equal to this. Is the derivative negative for x greater than equal to 1? Is it negative? So how do I know? Well, I look at this derivative. So let's think about e to the negative x. So, you know, I already graphed e to the negative x, right? Here it is. Here's e to the negative x. So if you go back to the graph, well, e to the negative x, that's positive, right? That's positive. That's always positive. You can see by the graph, it's above the x-axis for all the values, right? Okay. Well, what about 1 minus x? So this right here is positive. Now, what's the term 1 minus x? Is that going to be positive or negative for these values? So think about it. When I plug in 1 in here, what do I get? I get 0, right? But once I plug in something greater than 1, what happens to this factor right here? It becomes negative, right? You know, pick a value. What's a value greater than 1? 2, right? If I plug 2 in here, what do I get? I get 1 minus 2, which is negative 1. And if I picked 10, that's negative 9. That's negative. So I have a negative factor there for these values. What's a positive times a negative? That's always going to be negative. So yes, that's certainly true. This is going to be negative because of this. So there I could say, so therefore, my original function decreases. Excuse me. All right. So when you're trying to show a function's decreasing, you're just looking at the derivative. If the derivative is negative for the values of the series starting at the initial value to infinity, then you could say the original function decreases. Okay. So, all right, guess what? The series is positive terms. We showed that here. It's continuous because the domain of continuous functions is also continuous. And we just showed it's decreasing. So we did all three of these things. Right? So now we can apply the integral test. So what that means is we could integrate the function and go from there. So I got to integrate this function. So now I could say, all right, so apply integral test. So because I can apply the integral test, I could say, all right, so the integral from 1 to infinity of x times e to the negative x dx. I got to compute that integral. So I already mentioned this. How do you integrate this? Integration by parts. So if you forget how to do that, oh boy, set up your table. So what's going to go here? X. Because remember, integration by parts, you differentiate till you get 0. E to the negative x. All right, differentiate x, you get 1. Differentiate 1, you get 0. Integrate e to the negative x, you get negative e to the negative x. Integrate this, you're going to get e to the negative x. All right, so then you do the crisscross parts, right? So this times this times that. So then you get, right? So this is a positive times a negative, which is negative x e to the negative x, right? And then you're going to get negative times a positive, which is negative e to the negative x times 1 is e to the negative x, right? Now I would ordinarily put plus c here, but because this is a definite integral, right, I'm going to put bounds here from 1 to infinity. Now remember, this is an improper integral, right? This is an improper integral. So I guess I should have done this first, but I'll do it now. I have to rewrite this as what? I should have done it first in hindsight, but it's okay. I could have rewritten this as, since this is an improper integral because of the infinity, right? I have to do what? I have to rewrite this with a parameter, right? That's what makes it improper. So I got to rewrite this as the limit as b approaches infinity of the integral from 1 to b of x e to the negative x dx, right? So technically should have done that first, but I didn't. And then from here you can actually integrate, and then, all right, so now that I have that, let's come up here and replace this with this notation. So I'm going to have the limit as b approaches infinity of negative x e to the negative x minus e to the negative x from 1 to b. All right. So yeah, I'll just make a reference to that. All right, so when you go through this computation, right? So just pop in the bounds. So when you pop in b in here, you're going to get what? Negative b e to the negative b minus e to the negative b minus the quantity. When you pop 1 in there, you're going to get negative 1 times e to the negative first, which is negative e to the negative first, right? Minus e to the negative first. Okay. All right, so now just compute this limit. So when you do this, what does this go to? So what does this go to? So if I rewrote this as 1 over e to the b, right? And as b goes to infinity, this is going to be 1 over infinity, which goes to 0. Same thing here, right? Same thing there. So this is going to be 0. This is going to be 0. So this is going to be negative infinity times 0 minus 0, which is what? This is going to be 0, right? This whole thing is going to be 0. So when you go through that, that's what you're going to get. This whole thing is going to go to 0. So all I'm going to be left with is, so this whole thing is going to go to 0. So all I'm going to be left with is this quantity. So I have minus e to the first minus e to the negative first. I misspoke there. That's minus e to the negative first minus e to the negative first, which is minus 2 e to the negative first, right? But I have a negative preceding it. So it's going to become positive 2e to the negative first. Or, in other words, 2 over e. Okay. So 2 over e, that's the number. That's the number I get. Now, let's look at the conditions for the integral test. What did the integral test say? If the integral converges, then so does the original series. If the integral diverges, then so does the original series. Well, what did this integral do? We got a number, right? So, since we got a number, 2 over e, the integral converges. So what can we say? So since the original integral converged, right? Since this integral converged, we could say the original series also converges. So since this converged, we could say, therefore, the series k equals 1 to infinity of k times e to the negative k also converges. And I'm going to make an important note here. Whenever you do a test for convergence or divergence, you should always cite the test that you're using. So in this case, this converges. I'm going to say, what test did I use? I used the integral test. So I'm going to say this converges, and I'm going to say this converges by the integral test. That's it. So we successfully used the integral test. Since this integral converged, we could say that this series also converges by the integral test. And that's it. That's the integral test. That's how we do it. There's a lot to it. You know, there's 3 things you have to check for. If it's a positive term series, if it's continuous, and it's decreasing. Then you could do this. You have to check these first before you do the integral test. Now, I want to make a note. I want to make an important note here. This is very important. This value right here is not the value that this series converges to. The series does not converge to this value, 2/8. All we know is that the series converges. We don't know what it converges to. We don't know what it converges to. Because remember when we first started this chapter, or when we started looking at series, I said that most infinite series, we don't know what they converge to, unless it's geometric or telescoping. We can only determine if they converge or diverge. We knew that this test converged by doing the integral test. We know that this series converges, but we don't know what it converges to. So I want to make a note here. I'll squeeze it in down here. Note. We only know it converges. We don't know, I'm kind of running out of space here, we don't know the value. We don't know the value. So this right here is not the value it converges to. This is just the value of computing this integral. All we know is that series converges. That's it. So, you know, that's the general idea for the integral test. That's what you want to do, but it's really not that hard. You just go through all the potential steps for doing it, but that's really it. So in the next section, we're going to look at, we're going to start looking at other types of series tests. We're going to start doing another one. It's very useful. It's called the comparison or the direct comparison test. So that's it for this one. Pretty straightforward. But there's a lot to it, but it's not too hard. It's really not too hard. There's a lot of steps you need to consider before doing it, but other than that, it's just a lot of busy work. So, when it comes to the integral test, that's it. So in the next section, we're going to add to our list here. We're going to look at 2 more tests in 10.4. We're going to add some more tests to this list, and that's what we're going to do in 10.4. So that's the end of the video.